Welcome everyone to the 5th installment of the IK Rigs miniseries. So in the previous videos we've done a lot. We've done our hips, our legs, our feet, grounding. We've done everything from the hips down, and we even did the limbs when we were dealing with the legs. So we had the arms moving along with the legs in that second video, I think. So now we need to connect both sides of the body, which is through the spine. And the spine was the one part I had the most difficulty getting just right. And when you start looking at it in the mirror and things like that, you start to see how the spine really works. And one of the most crucial things that we need, there's two crucial points that we need to take into consideration when we're dealing with the spine, especially if you see how things work. When your hip moves a lot side to side, sometimes you'll want your spine to be stable, like your upper body to be stabilized. So if you're doing like a catwalk where a girl's legs or like her hips sway from side to side, but her upper body kind of is stable, it's not swaying all over the place either. It's nice and stable. It's just the lower body that's swaying. The first bone of your spine that connects to the hip is very crucial. It's what stabilizes the upper body. So you have to take that into consideration. The first bone is very important. And the second crucial point is the final bone of the spine. The final bone right here basically connects your shoulders and your arms, your neck, everything else. It basically is the final bone that kind of controls your entire upper body. Any bone between basically your final bone and the last bone, anything between is just extra bones that get you from point A to point B. And after all possible attempts at this, the simplest solution is interpolation. So if we take IK information from our first bone and then have a second set of IK information for the second bone, if we interpolate from A to B and just fill in the remaining bones with that interpolation, we will actually get the final bone where it needs to be, which is the main second focal point, really. Like I said, the second focal point is the upper body, because you want where your upper body is going to go. And anywhere your upper body moves, your spine just naturally curves together. Even if you're twisting, it's not like your chest, your ribs twist by itself. It's everything in your spine. You know, there's like 10 degrees, 10 degrees, 10 degrees. It's an accumulation of rotation. So that accumulation of rotation is what gets you to that final like twisting or bending aspect of it. And that's why I say it's interpolation. We know where we're starting from. We know where we're trying to get to, and we just interpolate from A to B. And that's really how a spine works. And that simple idea is how we just should translate it into code and mathematics. And there's a couple extra little tidbits I'm going to explain as we go along that I came into the solution. So we're going to go straight into the code, and I kept the explanation down to 3 minutes, which is good. I recorded this video a few times, and I usually make this explanation very long. One change we're going to do since the previous videos is we're going to add some new features. I added some new features to my pose animator. I forget what these numbers mean, but I just some quick hacks I did. So this way my pose animator would stop animating the characters walking forward. I want the characters to stay in position. So I just added these little bits and features. So this way the animating character can stay in place instead of moving forward. So this way we can kind of see things working a lot better instead of the character moving forward and then resetting back to origin and back, looping like that. So basically we get rid of all X and Z movement and we only keep our Y movement. And that's what these all settings are. Let's see, what else? So for our spine, we're going to have some new data that we want to add to our IK pose. And then here's our spine, very simple. And it's going to be an array of 2 points. A spine can have anywhere between 2 bones to as many as you need. Typically, especially with Mixamo, you always find 4 bones. I've seen some tutorials about like rigging, and a lot of animators say, especially if you're dealing with low poly, stick with 3 bones, because in general, a human body tends to only have about 3 points of rotation when it comes to the spine, when you really need to control it through 3D animation. So like I said, you'll normally see somewhere between 3 and 4. So that in-between point is where we're going to interpolate. But like I said, at minimum, you're going to have at least 2 points. You're going to have the part that attaches to the hips and the part that attaches to the upper body, like your rib cage or something. So it's going to be an array. So it's going to be A and B. So we just 2 points of critical contact that we need on the spine. So that will be the first part of the spine, and that will be the second part of the spine, and we're going to interpolate these two values. And the values we're using is swing and twist, just like all the other videos. We've done a lot of versions of it, but we're going to do it like that. But there's going to be a big difference. We're going to change how the data works. So just like all the other videos, we're going to learn how to compute the IK information. That's the first thing. Compute the IK information. It's quite a bit in here. Wait a minute. Let's see. Oh, that's applying the spine. We're not there yet. I'm like, wait, that's so much code. Computing it. So we're going to do the computing through our IK compute class. And in here, in the other videos, we had a to-do spine between like the limbs and the hips and between the arms. So now we're finally here. We're finally going to do it. And so again, just like the other times, we're going to pass in our rig, which chain of IKs we were dealing with, or IK pose. And we're going to just pass in the IK pose object in general, and just that object will just look at the spine property of the IK pose. And we then define our swing and twist rotation. And if you notice, it's different. Normally we deal with swing being the forward direction. We assign it the forward direction, and then our twist we assign the up. In this case, we're doing swing is the up direction and twisting is the forward direction. Now, this is the one thing I kind of changed, and that's why I kind of wanted to make these functions configurable, defining different ways to choose what the universal direction is for every animation, or for basically the universal direction for the animation system, not the animation specifically. All animations will follow the same rules. So why did I choose up and forward? Like I said, the first bone of the spine is what stabilizes everything. And to be honest, if we make the up direction being our main direction, it actually makes it a lot easier, and it does a lot better job of stabilizing the first spine bone to the hips. Like I said, if the hips are swaying like crazy, that first bone is what stabilizes the rest of the upper body. So if I use the up direction, since that bone is pointing up anyway, I should define that as my swing. So this way I have this like nice swing value that can go. I can go this way, that way, all way. And then the twisting is like secondary. It's like when it comes to the spine, swinging is, I think, is the secondary value as opposed to the twisting is the secondary, and swinging is the most important. So having that swing being pointed up actually gave a lot of stability, because I tested a bunch of animations. There's a catwalk that's really crazy, and actually when I had problems, I figured that having the up direction as the swing direction actually improved the stabilization of the upper body connected to the lower body, and that's one thing we always keep in track of. So that's why we're changing it up, and it's important to realize that our Quintorian inverse direction can be defined any way we want to that makes the most sense or gives us the best results. And like I said, when it comes to spines, that is the best way to do it. Like I said, there is not really a lot of code to it. It's very, very simple. So I'm going to create like a simple array, and I'm going to get the first bone and the last bone of the chain, because that's really all I care about. Just the two things. And I'm going to compute the Quintorian inverse. Granted, these things can be pre-computed, so this function could be a lot smaller if I have these pre-computed. And just like the other functions, just like in the previous videos, we grab the bone information. We need the bind and the current animated pose. Again, we create those inverse directions by using the information. Like I said, look and twist are the exact same functions, but the values we pass in are different. So the spine and the look twist that we did for most of the other bones, It's essentially the exact same thing. The only difference is the spine does it in an array fashion where look twist does a single bone. So it's pretty much a copy of that function, but on an array. So yeah, you grab, inverse, get the pose, save it, done. Get the data, inverse, get the value, save. We're done. It's the same idea. So like I said, we get the alternate directions. We recompute those directions based on the world space position, rotation on our bones, and then we can call it a day. And if I want to, I can just debug the results, refresh, and that's it. So all said and done, that's the first bone of our array, and over here is our second bone, and we have one bone in the middle. So this is actually 3 bones. I keep thinking 4 bones because the hip is kind of attached to it, but when we treat it as a chain, we don't use the hip as a chain, a part of the chain. So those 3 spine bones that are connected to the hips should be considered the spine, and hips should never really be part of the spine chain, because we need that chain to stabilize itself in relation to the hips. So I know in the beginning I said 4, but like I said, normally ideally you find 3, somewhere between 3 and 4. Okay. So, and like I said, that's information. That's all it is. Very simple. And then you save it into array. And like I said, our spine is an array anyway, so this way, just make it simple. Ideally, another way to go about this, if I wanted to, I can probably reuse this and just pass in the specific IK data to fill in automatically. So there's another solution. But like I said, since I'm prototyping, I kept trying to figure out different ways. This is how it is. But to make it more efficient, that's what I would probably do. It would just be 2 bits of code, look and twist, and then filling in each element of the array. So I would pass in this element, and it'll automatically fill in. Pass in this element and fill it in, and just put the first bone and the last bone in. If you want to kind of reuse code and not deal with additional functions that really don't need to. But like I said, this is this is what explains how you do it. Just go to first and last and done deal. If you, like I said, you can pretty much get rid of the whole for loop and then make sure look and twist functions well enough to work on multiple bones or single bones. Granted, this might be a change for version 2.2 or 2.5 for me. But as the initial thing, I like to keep everything separate and try different ways, because you never know. It's fun to prototype. This whole series is a giant prototype thing. So that's how we compute the spine. It's very simple. It's our look and twist with the values in reverse. And visualizing it is super simple. So we're going to get rid of this. And then after we're done dealing with all the feet and the limbs, we're going to do the spine. And the spine is super simple. Again, I use loops, of course, which does the same thing. Get the first bone, get the world position, get the IK information, and then just scale the look and twist direction to a small number, so this way it's not so massive, and use the world space position of the animation to illustrate it. So if I click refresh, there we go. So now we got all that IK information being rendered. So there's our point in 3D space. Yellow is going to be our twist, and cyan, I don't know how to say that one. This light blue, this ocean blue, is going to be our swing thing. 14 minutes. All right. So we know how to compute it, which is very simple by this point in time. And we know how to visualize it, which is very simple. Now we're going to know, how do we apply it? How do we apply the spine? And that's when we go to our apply function. So if I go to apply rig, there's our to do. Now it's been replaced again. So we're going to pass it the chain that we want. We're going to give it the whole spline array, and we're going to tell it that our up is swing and forward is our twist. So like I said, it becomes this universal direction of what the spine information means and how to apply it. And let's see, I write so much comments, especially for this tutorial, to make sure nothing loses in the caps. But pretty much, I think I pretty much explained all this already. All right, so we're going to have a lot of variables to deal with. It's like I said, we're going to deal with a loop, and we're going to do a lot of interpolation. So the first thing, and I think this one, does it use world space transforms? Yes, I'm using world space transforms instead of rotations. Again, like I said, we can simplify this by just using quaternions instead of using transforms. Transforms are great because then we can put points, like position points, in it. Because we're dealing purely with rotation, we don't know where everything is in world space. So for prototyping, this is great, but if I want to make something very efficient, I would actually convert all this into pure rotation and don't deal with actual positioning and scale, because transform deals with position and scale at the same time. All right, so we're going to need first we're going to get, since we're building up the pose, so every time we go through our apply rig, we are building up our pose object. There's a pose object in our rig that we work. So in the first video we did the hips, so now the hips have all the information set up already for the final pose. Then the limbs fill in, and then the feet get filled in. So now with the feet and everything filled in, now the hips have moved to a different spot, the hips have moved the spine into a different spot and everything else. So we have to build things layer by layer, and now it's time to deal with the spine. And once the spine gets filled in, then we fill in the arms, because where the spine goes is where the arms go. So we're constantly building up the pose. So we're building that pose up. So that's why we need to get the current world position or world transform of the pose that we're building from by using the bone. So now we know where its parent, like basically the hip. So it's basically where is the hip currently in world space based on the pose that we're building. Then we get the child transform, which is the current bone that we're dealing with. We're going to compute our IK look and twist. I'll tell you what that is. Again, this is not pre-computed, so we're going to compute the alternate directions for everything. Then the now look, this is basically the current direction that we're currently in at any specific time during the code. And these are just our trash variables that just to work with. My throat is doing bad today. Sorry if my voice isn't too good. Or I'm going to drink a lot, or I'm coughing. I don't have the corona, I don't know. Too much talking makes it hard for me to talk. All right, so we're going to have a loop, and we're going to loop basically every bone in our chain. So the first thing is that we're going to get the index of the bone that we're dealing with. The bone chain index is different from the bone index. So we want the index that's of our skeleton. Once we have the skeleton, we go into our T pose and say, well, I want that bone information because I want its bind information, its bind pose information. Then we're going to compute the T. The T value is going to be I over count. So we have a count up here, which is our chain count. So it says there's like, maybe, let's say that it says it's 3 bones, but we're going to subtract 1. So that means we're going to go 2, but it's going to be 0, 1, 2. And the reason why I'm doing that is because I want to use the count as to help compute our T value. And the T value is our lerp value, the value that we're going to lerp from one to the next, from A to B. So if we have 3 bones, the maximum number is 2, and that's why I say greater than or equal to. So if I'm on the first bone, the value is 0. So 0 divided by 2 equals 0. That means we're going to use 100% of the first IK information. That's exactly what we want. It's important that the first IK information is used untouched, especially since it's what stabilizes the entire upper body. Once I is 2, so it's 2 divided by 2, which equals 1, and that means we get to use 100% of the second IK value for the spine, which is important because that what controls the upper body, like the arms and the head. So this is why I do it this way. So this way, 0, and the final value has the maximum values. It would be 0 or 1 for IK. Now I have something here that we can do. I'll probably show you. Sometimes you can't notice the difference, but it can change how to maybe slightly improve animations if we have to, or it can be customizable as a feature. Because if we're going to, this basically does is a linear interpolation. So when we do the t-value this way, or I over count, we're interpolating from 0 to 1 in a linear fashion. Once I start doing like multiply by, or not multiply, double means power. So if I go, by the power of 2 or the power of 3 or power of the 4, we, instead of going into a linear fashion, we're going to in a curved fashion. So the more powers you do, the more curved we're going from between 0 and 1. So that gives us the ability where the center bones can interpolate less, and then have the main two bones be more solid to where they need to be. So this it gives you like this kind of control of how to interpolate from A to B, because you can use basically any tween function, except for spring stuff and bounce stuff. Just something that goes from 0 to 1, but at any specific kind of simple curve can really alter how the spine moves. All right, so that just keep that in mind, that you can control it, you can play around with it. That is another thing you can play with. All right, so we know what bone we want. We know it's bone. We know how we're going to interpolate, either linear or through a curve. And by the way, just to lean back, I think this might be called cubic. If you're dealing with tweening functions, I think this might be called a cubic tween. Square, by doing everything by squares, is like a simple curve. Any tween function, like I said, bounce or elastic or whatever, won't work very well for this kind of thing, but you can do like ease in, ease out, things like that, if you will. Like maybe an ease in, so this way, things curve with the curve more at the bottom than at the top. I forget how ease in and ease out works. But like any of those curves, you can use to control your spine if you really want to. All right, with that out of the way, now our IK look and our twist, which you've never seen in other videos, is really just the interpolation from A to B. So we have IKA and IKB, and we're just going to interpolate basing the t-value. So that's what that's what this is. That's all. It's just the interpolation. Then we're going to compute our inverse direction. We've done this a billion times already, I think. And now the next part is we're going to take our parent position, our parent transform, and we're going to add our bind local. So this way it's this bone, unrotated, untouched, but added to the parent's current rotation. So this way it's like a virgin rotation. It's virgin, it hasn't been touched yet, it hasn't been defiled. We have yet to defile this bone. So that's why so we're just taking this undefiled bone and bringing it into world space. So we know how to defile it wherever way we want to. Because we're ravaging beasts. We're horrible programmers. We want to ravage these bones. I don't know, I'm just being stupid. I think the longer I talk, the crazier I become. For all I know, I might have corona, I might actually have a fever. I'm not actually recording this at all. I have no clue what's going on in the world right now. All right, so since we're done ravaging, let's just get back to the point. So we got our bone unmodified existing now in world space. So we need to create our swing rotation. Actually, sorry. Well, first we need to get our location to generate our swing rotation. So we're going to take our world space and then pass in our alternate look, which is our swing value. So it's where we want to look, our main looking direction. What direction is the bone pointing now without? So I'm saying this is where now, where this one's current. Where is it looking at now? So we take the now and the IK. So we want to take the current looking direction and we want to rotate to the IK direction that we computed for interpolation. So we do that. We've done that already multiple times. So once we have that rotation, we add it to our untouched rotation. So now we finally swung it into the position we want to. Next thing is we have to figure out our now twist. Where are we currently looking at based on our twist direction? So again, we use our new rotation because now it now has been defiled. So now it's been defiled. Now that's been defiled, our rotation. How twisted is it after that fact? Actually, this analogy is starting to work out very well in a very twisted, sadistic kind of way. So this must be a fever dream. I don't know. I should do bloopers. All right. So the now twist, we know what direction we're pointing at. So now we know what the twist position. I noticed I have a bunch of debug stuff I haven't not been doing, so maybe I should do that. Why not? How about we just start doing that instead of me being a clownster? Oh, you know what? Well, I can't apply anything if I have nothing to apply it to. So let's bring back the Prince of All Saiyans. Refresh. There we are. So, yay, that's our point. Well, that was lackluster. It's just a yellow dot. That's probably why I just completely skipped over it. It was just lackluster. Yeah, that's all it is. It shows points. That's all it does. Okay. And then I guess over here. Oh, I have a break. Sweet. So we do the twist. So we know the twist direction. And then we go from our twist that exists now to the IK twist direction. And then we pre-multiply it to our defiled rotation. So we're going to defile it even further. Okay, so we're just going to keep with the analogy. And just for testing, I'm going to recompute the now twist because after I defiled it, it's more twisted. So I want to know what is its alternate twist direction. So if I do that, we can see it's not showing our well, it's only showing our twist value. So you see our twist value matches up. Yellow, our IK I believe is white, and then yellow is our current, and white is our IK. So that means the twist value is exactly what it is. And for the twist value to be exactly where it is, that means the swing value is exactly where it needs to be. If if the swing is wrong, twist is going to be should be wrong. Like it wouldn't match up with the IK direction at all. So there you go. So the first spine is perfect. And I guess if I get rid of this break, it'll continue on. So once we're done, we just get the invert of our rotation because now this is the complete final rotation that we need for world space. So this is what we're gonna want to save back into our pose. So we multiply it by our parent inverse, and by pre-multiply inverse of our parent, converts it to local space, and then we can finally save it right back into our pose. Now, instead of calling this function get world parent for every loop, I've seen that in some code before. I'd rather not recompute everything especially since I know rotation is the rotation we want to be. That is the rotation that bone is going to be. So I take the parent transform and I add it with our new rotation, and then we take the local bind space position and scale because I'm building this up as transforms instead of rotation. So simply it's mainly there so I can debug things, but again, like I said, you can just do everything in rotation, and you just take the parent rotation and multiply, not p-mul, just multiply by our rotation, which creates the world space parent rotation for the next bone in the array. So there you go. And basically, right here, I say if t is not equal 0. So if it's the last bone, t is going to equal to 1. Don't bother doing this, because if it's the last bone in the array, there's no point of doing all this extra math. It's just a waste. It's a waste of processing power because it's not going to be used. So if the interpolation is not 0, don't bother generating for the next interval, because we're at the end of the interval. There's other ways you can do it, but I think this, to me, there's the simplest solution without creating extra variables to keep track of. When say t equals 1, I know we're done. This is the end of the interpolation, because the final bone must have no modifications to it whatsoever. Multiplying anything by 1 becomes 1, or becomes itself, whatever you multiply by 1. So if I refresh, I don't know why it's saving here. And there you go, all 3 bones. Everything exactly where it needs to be, and that's interpolation. It's interpolating from bone A to point B. So there you go. That is it. And that's how you apply the spine. It's surprisingly, for all the heartache that I dealt with to do this, I find it funny that sometimes I go through like these crazy difficult solutions, and sometimes it's the simplest solution that works out. Granted, I had to realize that I had to switch over, from forward to up to increase the stability. But again, lerping is such a simple solution in my opinion. It's not even an IK thing, in all honesty. But I'm basically saying it's IK because all I have is directional information and then using that in a certain fashion. But that IK information is all in relation to the animation, so it's not like an end effector. So, but granted, it still does the job for what we need, and that's it. So the only thing left is see what the animation looks like. So all I have to do is switch out of mouse render to loop rendering, and I should get nice animation. And there you go. And you can kind of see how much the hip and the chest changes in relation. There you go. There's not a lot of movement to the hips. I think if you want to, like, where's the apply? So if I do something like this, the chest might change a little bit. Like it might take more. There's a little bit more movement because now we're curving it. So instead of interpolating the spine perfectly even, we're having the center interpolate less, and then the spine takes more of the rotation. Because remember when I said, like, your spine is the accumulation of rotation. So 10%, 10%, 10 degrees, 10 degrees, 10 degrees, and your final bone is like 30 degrees. So if I want to, I can probably like go crazy, say a power of 9, make a crazy loop. It's probably hard to tell because it's such a simple solution, but there's a little bit more movement applied to the final bone as opposed to anything else. So the center bones tend to be more still because there's less interpolation happening because of the curve. So like I said, you can really customize it. You can, like, this can become like an additive. It can become like an additive saying, okay, here's a configuration. So when you're dealing with spine, here's an additive. Increase the interpolation curve by a factor of 2 or a factor of 5, whatever. Or here's the tweening function to control it. And to enjoy it, because like I said, that's a very simple animation. Now, you know what? Let's first bring Roborex. Let's bring Roborex back into the mix. Roborex, I think, only has 2 bones. He only has the first bone and the second bone. And like I said, it works because it only has 2 bones, so it's only 2 points of transfer. So that first bone is really trying to stabilize itself from the hips. So there's not a lot of crazy movements. And the second bone is exactly where it needs to be. So that's really where it's going. So the upper bone, the final bone, your chest bone basically, is the one that's doing the swaying. So it's the final bone in that spine that's making the upper body sway back and forth. So if we want, we can get rid of the walk and do the, this is the animation that broke everything, that had to really figure out a solution on how to get the spine working. So as you can see, when it's animating the centerpiece, there is a lot of swaying. And if you don't do a good job of stabilizing, the upper body will sway more and left based on the hips. We don't want that. A nice simple way to test it is just by going to our apply and say don't apply at all. If we don't apply at all, so this is something what happens when you don't do a good job of applying and not stabilizing the animation. It looks a little janky. Because like I said, that first bone is what really stabilizes it. So you want to really make sure that first bone does a good job of animating in relation to the hip. So if I add the stabilization back in there, now the upper body is a lot more controlled. It's exactly where it needs to be. Let's see, let's add by a factor of 9 again. And see how the spine handles it. I think that like the first two bones don't do too much. I think a lot of more work is being done. It's kind of hard to tell. It's like, to me, it's like I need to run the two Vegetas and then see what the difference is to really visually see it. So refresh. 36 minutes. So there you go. And on top of that, we have Robo Dino doing a catwalk. He's got the hips, but as you can see, he's not swaying too crazily. It's all based on the upper body controlling itself and the lower body. Because his hip is all over the place. Like, because his is square, so it's very easy to see it like all over the place as opposed to Vegeta. His hips are a shape that's kind of hard to see the movement a little bit. But he's swaying just as much as he should be. But yeah, there you go. And this is the beauty of the IK system. This is like the reason why I thought this is great to implement and build it. Because this is a robo dinosaur. This animation, it was never ever meant for an animal with no arms and with like 3 bones. It's never meant for this. It was not meant for this. But by using the IK information, the animation is unchanged. We're not changing how the animation changes. It's just being applied through an IK algorithms of some form or another on a dinosaur. And it's beautiful. I love it. It's mathematics in its beautiful form. And I'm not mathematics, like I said, I never went to college, so I don't know what the hell I'm doing. So I'm probably a good example of maybe college isn't for everybody. You know, I've gone pretty far without it. It's all about hard work, man. All about hard work. So there you go. Almost 40 minutes to walk through how to make spines work in your IK rig. So we only got one more video left, and of course the only thing left to deal with is the head. And the head is really super simple. Again, it's just rinse and repeat of swing and twist. And so the next video is going to be short. So we're going to deal with the head in the next video, and we're going to actually add springs. Because I've done like, I think 5 or 6 videos related to springs and how to use them in various ways through positioning and rotation, and then actual bones to make jiggly bones and things. So we're going to do a jiggly bone. We're going to use our jiggly bone that we made many videos ago, and we're going to apply it to his dino's wings, fins, whatever you want to call them, and to his tail. Because, like I said, this animation is meant for a person, and it's actually meant for a female body. That's what it's really meant for. It's meant for a female body, which is always funny to see Vegeta sit there and strut his butt like that. It is kind of funny. The Prince of all sins. So since we don't have any animation of no information to how to animate the tail and his fins, we can then use springs to procedurally animate those bones in relation to how the rest of the body works. So that's going to be the next and final video. So I'm going to record that next, so I'll see you guys in a minute.